my name is Adolfo Matamoros. I'm a professor of civil engineering at UTSA. Today we're giving top billing to Reza Nazuri, who is, actually he graduated. He's a former PhD student and he's moved on to better things now. And I want to acknowledge also my colleagues, Fred Testic and Arturo Montoya from our department. So presentation today, we're interested in understanding a little bit better the nuts and bolts on damage that might happen in bridges. If we look at past events like Katrina, where there was significant damage to coastal infrastructure, the risk that we face in terms of hurricanes is just as big, or by many instances higher than we do from earthquakes, and I don't think we have paid enough attention to it. Certainly there's a lot of work to be done from the analytical perspective and new tools to be used to address that problem. So the focus of our work is estimating hydrodynamic response of bridges. When we look at the hydrodynamic forces on a bridge, there are a set of parameters that are going to affect how big is that force and how likely is the bridge to be damaged. Some of them are related to the water itself, the wave, the shape of the wave, the period, wavelength, the wave height, I guess in some context the storm surge as well, but there are also parameters that are associated with the bridge, among them the geometry of the bridge, the flexibility of the substructure, and others. Our development of design provisions for hydrodynamic forces, even though people have done efforts, I don't think we have invested anywhere nearly enough. There's a couple of approaches that are commonly cited in the literature by Douglas in 2006. It's a simpler approach to estimate hydrodynamic forces. And then there is the AASHTO approach in 2008. The equations are far more elaborate than the equations cited by Douglas. And I think we're still learning about how to best utilize those equations. So in the broad sense, if you look at the AASHTO provisions for the 2008 AASHTO provisions, which I believe were developed as the byproduct of a pool fund study, they identified two cases. They think of it in terms of uplift force and horizontal force. And these two don't necessarily occur concurrently, so there are equations for estimating the maximum horizontal force on the bridge and then the uplift force associated with that, and vice versa. You can estimate the maximum uplift force and the horizontal force associated with it. And the provisions would have you evaluate both cases to identify which one's more critical. And that's based on a given set of wave parameters, being wavelength or storm surge, wave height, and so on. So this is not the best simulation in terms of geometry and smooth, just to illustrate the point. Now we have newer simulation techniques, multi-physics models that allow us to simulate fluid structure interaction in a more complex way. In that simulation that you see illustrates the root of the problem. What happens during a hurricane is you get waves impacting bridges and causing unseating. And then afterwards you see a lot of damage. It's some simplistic way to approach this would be to say, well, you restrain in the horizontal direction and you're going to take away the problem. But that's not necessarily true. I mean, if we look at damage images after Katrina, there were spans that had some reinforcement through the connection, and the uplift forces were, it was ruptured. And so having shear keys is not a guarantee that the bridges will will subsist. And I think that that's something that we need to take to heart also when we're designing new infrastructure to avoid that problem. So as I was mentioning, the methodology that we chose, we are trying to take advantage of some of these multi-physics fluid structure interaction tools that are becoming available. There are techniques like coupled Eulerian-Lagrangian analyses. There are others that are available. So when we started this, we went on to evaluate a few and figure out what's the one that could yield the more immediate results. And we began to develop some high fidelity models, which we calibrated with some experiments that are out there. And eventually our goal is, like the previous speaker was saying, understanding a little bit better what the fragility is. So we can run arrays of simulations where we vary hydrodynamic conditions and we vary bridge geometries and different characteristics to understand better what is the type of damage that we can expect. You could also use that type of information to improve the way we design new bridges. So as I mentioned, the approach that we adopted was a coupled Eulerian-Lagrangian approach, and that means that we use different sets of equations to model the fluid than we use to model the solid. If you're a structures person like myself, you're very, very comfortable in the Lagrangian domain and are quite comfortable with equilibrium equations. We do a lot of that here in ACI. But folks who work in the fluids domain, they use different coordinate system. They use a Eulerian coordinate system. It's a little bit different. There you work in terms of equations of state, and you have different sets of equations. So a lot of analyses that you see today would have these two approaches maybe implemented separate from one another. So somebody would do a Eulerian type analysis assuming that the structure is rigid, and then estimate forces and pressures on the face of the structure, and then come to a physical model, Lagrangian model, and impose those forces and then calculate. What we're trying to do is we're trying to couple the two so solve simultaneously, and so the flow and the deformation in the structure can change in response to changes on each other. They will interact with each other. So as I was mentioning, these two approaches are a little bit different. In a Lagrangian mesh, the approach is that the points in the mesh are attached to material, and as the material deforms, so does the mesh. The mesh deforms with the material. In the case of Eulerian analysis, the approach is the opposite. You keep the mesh in place, and materials flow through, and you track velocities for the most part as they move through the mesh, or particles as they move through the mesh. And so Lagrangian meshes are very good at dealing with small deformations. Eulerian meshes are much better suited in situations where you have fluids, where there are very large deformations, or even in solids, when you think that the deformations are going to be very, very large. Because every one of us who's done a little bit of finite element work, or even simpler analysis, you understand that in your Lagrangian mesh, as things begin to deform excessively, all kinds of numerical problems arise. So that's the advantage of Eulerian meshes over Lagrangian meshes. These are some of the features that I was mentioning, probably a little bit late in the day, so we'll say that I already covered that. And I'm going to show you some of the simulations. This is a very simple simulation just to illustrate what's going on with the fluid, the flow. So model the effect of both the fluid and the solid it is important that you model the velocity field appropriately, and then that your fluid is able to adapt to changes in the shape of the solid, so you get proper flow around the solid. And as you can see, if you look at the bottom of that I section, the fluid behavior here is highly turbulent. It's very, very difficult to simulate with a simple model that type of interaction. At the same time, we're concerned about what is happening in the solid. So in this case, we're amplifying stresses significantly, but the point being is that as the fluid impacts the solid, then you calculate stresses and deformations in the solid. So the two are speaking with each other in real time. So I think one of the biggest challenges that we face up front is to develop some confidence in these models before we go out and extrapolate and look at a wide set of parameters and variations, and then we have to be able to trust what the numbers are going to give us. And that's one of the motivations for using this type of analysis. Fluid structure interaction problems are very, very difficult to simulate in the lab. They're very expensive. Flumes are not big enough. So they typically suffer from two problems. The scale factors are very large. Structures are very, very small compared to prototypes. And of course, there's some size effects that are involved, and that limits the ability to project what you learn from flume tests to an actual bridge. And then, of course, the other problem is people typically don't simulate the substructure in their flume test. Everything is rigid and fixed, so you're missing what might be a very important dimension in the response of the bridge. So on that note, we looked at some tests that have been done at Oregon State, some of them funded by the National Science Foundation, where in their flume they simulated the impact of a wave on a timber wall that was instrumented. They also have results from, there's a study that was done on a 1:5 scale model of the Escambia Bay Bridge that was damaged during Hurricane Ivan, where they actually, and let me show that one right here, also added some springs to the bridge to study the effect of the substructure flexibility on the total response, which is very seldom done, and certainly it wasn't done in the development of the AASHTO equations in 2008. So we built a finite element model of that bridge. As I mentioned, this is a coupled Eulerian-Lagrangian approach. So the solid is measured in the Lagrangian domain. The fluid, define a Eulerian domain. We define boundary conditions that allow water to come into our model and to go out of our model. And this shows I hope. Oh, there it is. So a typical model where we set the storm surge level right below the bridge girder, and then we simulated a wave that impacted the bridge. So it may seem simplistic when you look at it, but we spent quite a bit of time learning, for example, how to simulate waves so that when we simulate them, they have the velocity and the amplitude and the wavelength that we actually intend for them to have. So there's quite a bit of trial in understanding a few tricks of the trade in order to get this thing to work. So when we first run our first series of simulations, just trying to compare what happened in the Oregon State model with our computer models, we computed horizontal and uplift forces. In, you can see there, horizontal force for this particular simulation run almost 60% of the bridge. The uplift force run exceeded 100% of the weight of the bridge. And so these numbers were consistent with what was measured in the last particular set of wave impacts. So that was a first step in trying to develop some confidence in the way that we're doing our simulations. Then we got curious about investigating what happens when you actually include the substructure. Because when I, my training has been in the field of earthquake engineering, and you're trained to think of this as a dynamics problem in terms of the structure. The structure is subjected to a certain impact force, and then it oscillates. And so it stands to reason that the magnitude of the forces that the structure will see, it has to be dependent on the dynamic properties of the structure. And if you negate the substructure, and that is flexible enough, then you're neglecting an important part of the response. So this shows simulation with 3 different wave velocities. So what I'm showing here are results from a few runs that we've done. So certainly you can see the difference in the amplitude of the displacement as the wave velocity increases, and how much more displacement you'd get in the bottom simulation, which is 1.5 meters per second, versus the top simulation, which is the slowest wave speed at 1/2 meters per second. If we look at this in a more static terms, you can see the red curve is the fastest wave velocity, and then the black curve is the slowest wave velocity. So there's a significant difference in the amount of displacement that the bridge oversees depending on wave velocity. So that's one of the things. And then, of course, there are differences as well in the magnitude of the uplift and shear forces depending on the wave velocities. But the correlation seems to be there. Faster waves have a bigger impact, and then they generate larger uplift and horizontal forces. We looked at a couple of other bridges that had been damaged during storms, not only the Escambia Bay, but we looked at St. Louis and Bilaxi Bay bridges. It's a 20-minute endeavor, so I don't want to bore you with an endless stream of results. I'm just going to show a few for the Biloxi Bay Bridge. In this case, we started looking into what happens when you change the flexibility of the foundation or the substructure, not the foundation, but the substructure, by changing the length of the piers. And so these are the results that illustrate, again, in terms of displacements, for the same wave velocity, you get significantly larger displacements for the substructure when the substructure is more flexible, which is to be expected. Then, of course, the question arises, what does that do in terms of forces? We need to start this one. And you do see differences in forces, and people have mentioned that, namely that as the structure becomes more flexible, then there's less of an impulsive response, and things tend to simmer down. So including that flexibility is actually toning down the magnitude of the forces. We still struggle, and we're working really hard to figure it out, and this happens in the tests. You see that there are really large spikes. And so if you go to the AASHTO formulation, for example, they will take readings from flume tests, and when you see a spike like that, they would break it down into what they call a quasi-static portion of the total force, which is maybe the more gradual wave-like measurement of force. And then in the they'll call that a slamming component, and the AASHTO 2008 expressions give you expressions, both for the quasi-static and the slamming component. And so from my point of view, in terms of the modeling of this, when I see spike like that, like those, they always make me very uncomfortable. I don't know if these are fiction of numerical noise that is going in there, or how much of this is real. So we're trying to work to try to ascertain that, because it is inherent, is part of, and that's what makes simulating this problem very challenging. You do see those spikes also in the flume test. It is not only in the finite element analyses that they show up. But if you get past that, there are differences in the response. You know, in this case, we're intrigued because the intermediate height seems to be the one that responded more in terms of shear. We think that might be showing that the periodicity of the bridge with respect to the duration of the impulsive force might be having some effect. And we can't assume that it's going to be the same for all bridges. It's going to depend on the flexibility of the substructure. Some of them are going to react more, some of them are going to react less. And we see the same type of answer that we get with the uplift forces. You also see that effect where some geometries seem to react more than others and is not necessarily. So that's something for us to work on more and refine and try to understand. Then there is, and we asked that question, and we have other efforts ongoing, trying to understand how our simulations fit with respect to the Ashton equations and the Douglas equations. So there's what we get versus what design engineers would calculate. And you can see that there are instances in which we exceed by a little bit. There are other instances in which these spikes exceed by a lot. And so that also lead us to a little bit of scratching our heads, how big of a risk that represents in terms of the stability of the structure and the damage that it might perceive. That's part of a different effort. We have obtained through Louisiana data set about 600 bridges, and we're trying to just do analyses based on the Ashton equations to understand how those bridge geometries respond, the equations for uplift and horizontal force, to different combinations of hydrodynamic conditions on the waves. And we're finding out very interesting things. I think one of the issues with the Ashton equations is that they were calibrated on the basis of the Escambia Bay Bridge. There was one set of flume tests that were used primarily to simulate that. And I don't know that, I think we need to do more work on validating them and understanding them when there may be circumstances where we might get in trouble. So my last slide, I promise, I know my time is up. We think that we are obtaining some interesting results with this CEL technique. We certainly, I think, need still to do some more homework to feel more confident about it. We think that accounting for foundation flexibility did in fact have significant effect on the hydrodynamic loads and the response of the bridges. And you know, to sum it up, we are scratching our heads a little bit about those big spikes and what to make of them. I'd like to conclude by thanking the folks that made this study possible. We got funding from TransEd, the Transportation Center for the Southeastern United States, and you out with the use of the computer cluster SHAMU. So with that, I'd like to conclude, and I'll be happy to answer any questions.